physics students. This is my dad showing how to find the acceleration of the box as it slides down the ramp. Yep, I'm very descriptive, and he's going to help you out a little bit. Hope you enjoy this.
Thanks, Hannah, for that wonderful introduction. This is a problem involving sliding friction, and it's a typical problem in introductory physics classes. If you can understand this one, you really have a good grip on using Newton's second law to solve motion problems. So here's my sketch. Shows a box on an inclined plane with an angle of 30 degrees, and we assume there's some friction. The coefficient of kinetic friction is 0.3, and the job is to find the acceleration of the box as it slides down the ramp. So here's the way we're going to do it. And before we do anything else, remember, there's a couple things we got to remember, is that the force of kinetic friction, sometimes called sliding friction, is given by F sub k for kinetic friction, and we write that as the coefficient of kinetic friction, mu sub k, times the normal force, F sub n, and we'll need to use that later. Okay, we always start force problems by doing a free body diagram. And so that free body diagram we're going to draw separately and make the mass, the box, a big point. And so we'll show the ramp with a dotted line here and draw all the forces that are acting on the box on this diagram. And the first one that we know about is the force of gravity pointing straight down, F sub g. We also know that there's a normal force because the box is sitting on the ramp and the ramp is pushing on it normal or perpendicular to the surface, and that's F sub n. There's one more force because as the box slides down the ramp, it's opposed by the force of friction, the kinetic friction force that points up along the ramp. Now what we have to do before we can use Newton's second law for the x and the y components of these forces is we've got to break them down into their components. And to do that, we have to define a coordinate system. So I'm just going to show a coordinate system like this, where we put the x direction along the ramp pointing down and the y direction perpendicular to the ramp. And this is typical for inclined plane problems. And I also want to put in the problem where the angle theta is. And that's the angle that the plane makes with the horizontal. Okay, so first, break the forces down into their components. And to do that, we've got to take, let's see, the force of friction and the normal force are already pointing along the axes. So those are easy. But the force of gravity, part of it is along the x direction and part of it's along the y direction. So we need to sketch in a triangle, a right triangle, where the two sides of that triangle will point one along the x direction and one along the y direction. So that's our right triangle, and the force that's along the x direction is the x component of the force of gravity. We'll call that Fgx. And the other one we'll call Fgy. And really important here to break these down into their components is to figure out that angle theta, that 30-degree angle, where is it in this right triangle? And after staring at it long enough, you can convince yourself that that's the same as the upper angle in the right triangle, theta, right there. Okay? So, once you know that, now, to break these forces down at their components, we look at the sine and the cosine of that angle theta. From the right triangle, we can see the sine is the opposite side over the hypotenuse, so that's Fgx divided by Fg. Fg is the hypotenuse of that triangle, the whole force of gravity pointing down. And so from this, right away, I can say that Fgx is Fg sine theta. That's important. And then we move on to the cosine, and by doing exactly the same thing, we can see that the cosine of that angle is Fgy. It's the adjacent side to the angle, Fgy, divided by the hypotenuse, or Fg. And one more time, we can solve for the component Fgy and that's equal to Fg cosine theta. All right, now we're done with the preliminaries, and we're ready to start using Newton's second law. And for problems like this, we have to write F equals ma. We know that that's the second law, but we have to write down part of it along the x direction and part of it along the y direction. So here's the way it works. We write down the summation, which is this Greek letter sigma, the summation or the sum of all the forces along the x direction. What's that equal to? Well, we can see from the sketch there's two forces along the x direction. There's Fgx that points along the positive x direction, and then there's F sub k that points along the negative x direction. So this is Fgx minus F sub k. Those are the only forces or components of forces that point along the x direction. And Newton's second law says add up all those forces, and what you get is the mass of the box times its acceleration along the x direction, its acceleration along the ramp. And that's what we're trying to solve for. We'll get to that in a minute. Can we do anything more with this? Sure we can, because we know Fgx is Fg sine theta. And remember that Fg, the force of gravity, always has a magnitude that's given by the mass times g, the gravitational acceleration due to the Earth. So we can write down Fgx is Fg sine theta, or it's mg sine theta. Right there. And minus, now F sub k, the force of friction, is equal to the coefficient of kinetic friction times the normal force. Okay, we substituted in for those. Those are equal to ma sub x. And we're done with this right now. We can't solve for a sub x by itself because we don't know the normal force. We're going to have to figure that out separately. We do know the coefficient of friction, we know g, we know the angle theta, but we don't know the mass and we don't know the normal force. So we move on and do the same thing for the forces in the y direction. The sum of the forces in the y direction, well, that's just the normal force. That's in the positive y direction. So that's F sub n. And in the negative y direction is Fgy, the y component of the weight or the gravitational force. So that's minus Fgy, and that's equal to mass times acceleration in the y direction. Okay, so now we can substitute in. We don't know the normal force, so we'll just keep writing that as F sub n, but we do know Fgy is Fg cosine theta, or mg cosine theta. And now here's a really important part of this problem. What's the acceleration along the y direction? Well, the box slides along the x direction only. It doesn't move along the y direction. Okay, it doesn't pop up off the ramp and accelerate. So its acceleration along the y direction is 0. And you got to think about that, but that's really important here, because if we realize that, then we use this equation to solve for the normal force. F sub n is now equal to mg cosine theta. And that's a big part of our problem, because what we can now do is take that and plug it into the equation that we got from the x components of the forces. We can plug it in up here in the equation where we see F sub n. So let's rewrite this equation and plug it in. We have mg sine theta. All right, now here's where we're going to make a substitution. Minus mu sub k times the normal force is mg cosine theta. And altogether, that's equal to m a sub x. A sub x is what we're trying to solve for now. And right away you can see there's a factor of m in all three of these terms, both sides of the equation. So if we divide through by m, the mass drops out. And that was why we weren't given any information about the mass. We didn't need it. It drops out of the problem. And so right away, we've got the solution right here, a sub x. I'll just turn it around. A sub x equals g sine theta minus mu sub k, the coefficient of kinetic friction, times g times cosine theta, and that's it. And I'll let you plug the numbers in, but the numbers, if you plug in 9.8 for G and you plug in 0.3 for the coefficient of kinetic friction, you get the answer of 2.35 meters per second squared. So that's the way we solve problems involving Newton's second law. This is kind of a complicated problem because we had to use the sum of the forces in the x direction equals max, the sum of the forces in the y direction equals may, and then we had to put those two equations together. But these steps are important, and if you can follow this problem, and if you can do this, you'll be able to solve just about any problem involving Newton's laws.